Hello, everyone. Welcome back to Physical Geology 1403. Today, we're learning about, drumroll, earthquakes and plate tectonics. We've talked a little bit about both these things already throughout the course, but today we're going to dive a little bit deeper on those. I am not going to linger for too long on lecture today. It is the lab exam day, so I'm going to try and give my in-person class here at least an hour and a half or so to work on that. Those of you that are taking this class online, obviously today or before the due date of whenever you're watching this, whichever class section you are watching this is when you should finish that lab exam. I'll talk a little bit more about the lab exam after today's lecture before I end the recording. Okay, some quick announcements. Your final is opening 1 week from today and will close 24 hours later on Friday, okay? That is, if you're watching this on a Thursday later in the future, okay? It will close 24 hours from whenever it's assigned, okay? But for right now, for those of you watching this right now, that is 1 week from today it will open, and then 24 hours later it will close. Please plan accordingly. The way that I do this is most people will try and give you your finals so that it closes on Thursday. I try and give you that extra day because most people try and turn your grades in last minute on Mondays. I turn them in on Friday, okay? I've never had a problem. No one's ever had to come to me and say, hey, your final grades are overdue. And I plan on keeping it that way. I get your final grades turned in a timely manner, which is by Friday evening. That means that I need all of your final exams turned in by no later than, say, noon on Friday. That's about when I usually close the class and start tallying up final grades. Okay? Any questions about that? No? Great. Any questions about anything, really? You just took exam 2, right?
So that when you say close the class, then I don't mean everything.
Everything.
Apart from that.
I will close the class at about noon on Friday. You will not be able to turn anything in. You won't even be able to open the class. You'll go into Blackboard and you won't even see the class there while I am tallying up final grades. I will reopen it afterwards so you can see your final grade. Whatever grade you see when I reopen the class, that is your final grade that I have already reported by that point. So if you are planning to turn in anything, do it well before then, okay? Good. Yeah. All right. Any other questions? So lab exam today, lecture on Tuesday or the next time we meet, and then the time after that is our final exam review / final exam. Good deal?
Will our final exam also be physical? Or
No. Your final exam will be the same format that exams 1 and 2 were. There is no lab content on your final exam. Talk more about that on the day of, though. Okay? Okay. Let's jump in. Earthquakes. Someone tell me what an earthquake is.
A movement of plate tectonics.
Movement of plate tectonics. There's a lot of keywords there. All right. Basics. Break it down. What is an earthquake? Huh? The trembling of the land. Okay, the earth is shaking, quaking, right? It's moving. How many of you have felt one? If you live here in Odessa, you have felt at least 3 over the last year and a half. 3 that were large enough for us to worry about anyway, or to think about, to actually notice. There are earthquakes constantly going on, but it's very difficult for us to feel anything below a 2 or 2.5 on the Richter scale, which I will tell you about the Richter scale today. Okay. An earthquake is what happens when there is some movement inside of the Earth's crust or just below the Earth's crust. What would cause this movement? Well, someone mentioned plate tectonics a moment ago. That is most certainly a cause of this. But also, when we learned about metamorphism, we learned about stresses that occur inside of the rock underground, right? Differential stress, for example, unequal stress coming from different directions. That stress is going to build and build and build. What happens if I were to hold a stick in my hand and slowly exert stress on it? At some point, it's going to what? Snap. It's going to break. Rocks do the same thing. When that rock breaks, when that layer of rock snaps, when that energy is released, that energy that has been built up, we call that elastic energy. We'll talk more about that in a few minutes, okay? It has to be released. And how is it released? In all directions. If I snap my fingers, y'all hearing that noise? You're hearing that noise because the noise is being generated right here at this point in space, traveling through the air at the speed of sound, right? Reaching your eardrums and being processed by your brain. It's traveling in every direction, though. If one of you was on the ceiling, one of you was on the ground, one of you was on that side of the room, and one of you was on that side of the room, and I snapped my fingers between all four of you, you would all hear it. Why? Because this sound wave is not traveling in any given direction stronger than the others. It's traveling in every direction. Okay? Like a sphere, like an expanding sphere of noise. Earthquake energy is the same. It expands in all directions from the location where it is released. That earthquake energy manifests on the surface as a wave. Picture, if you will, you're standing over a pool and you've got a piece of gravel in your hand. And even though you know it's extra cruel to whoever owns this pool, oh man, they're going to have to go in there and get that gravel out or else it'll mess up their filter, right? You drop that gravel in the pool. What's it going to do to the water? As you drop this object in the pool, what does the water do?
Splash and ripple.
A ripple. A ripple spreads out. Why? Because your rock is imparting energy to that water, and that water is taking that energy and moving out in that two-dimensional surface that we see, the surface of the water. But imagine that same effect in 3 dimensions. It's a sphere of expanding energy. But when it reaches the two-dimensional surface of the planet, right, it's going to manifest in that sort of ripple shape. A sphere, an expanding sphere, is 3-dimensional. On a 2-dimensional plane, it's an expanding circle, right? So we've got these circles of energy expanding outward, and that's what makes our earthquake waves that cause so much damage. Now, where that first movement takes place, where that energy is released, we call that the focus. It is the origin of this energy. The movement happened there. Now, when you hear on the news that there was an earthquake and yada, 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 they don't really tell you about the focus, okay? It doesn't really matter to anyone in the media what the focus was. How deep was the focus? No one really cares unless you're a geologist, right? I get reports on every major earthquake that happens. I get information about where the focus is. That's interesting to me, but CNN doesn't care, right? So they tell you about the epicenter. What is the epicenter? Well, if the focus is the center of that 3-dimensional sphere of energy, the epicenter directly above the sphere is the center of the 2-dimensional expanding circle of energy on the surface. So the epicenter is always directly above the focus because that's where the sphere first makes contact with the surface, right? Epicenter, radiating energy from that. It's not that the movement occurred on the surface. That's just where the first indications of that energy manifesting on the surface happened. Okay? So if you see in the news that there was a 5.3 earthquake 17 miles north of the Synergy in Odessa, that's just where it was for the energy first was made apparent on the surface. It's probably 20 kilometers or so below that, right? Maybe less than that, but you get my point, okay? And then obviously the waves are radiating out from the focus and then on the surface from the epicenter. Okay, we'll talk more about those waves soon. All right, so let's talk a little bit more about what causes this earthquake. All materials have breaking points, right?
Yes.
The higher the breaking point of a material, the more stress it can absorb before breaking, right? Think about a rubber band. Here's our good friend, the rubber band, okay? You're stretching it, and the material is stretching and stretching. And as it is stretching, what's it doing? It's getting more and more energy until finally the energy pent up in that material is too great for the material to handle. Your rubber band snaps, right? Either that or the friction between your finger and the rubber band is no longer greater than the force trying to pull the rubber band back. In either case, your rubber band will snap back to its original position, releasing all that pent up elastic energy. That's the same thing that's happening to rock. This stress, which we will often refer to as shear stress, by the way, okay? Shear stress is causing all this pent up energy to build and build and build and build and build and build until finally it slips. If you want to actually get a physical example of this, okay, everyone put your hands together like this. Hands flat together. Push them together as hard as you can. And then try and slide your right hand forward. Eventually, like, it's going to be difficult if you're really pushing them together, but eventually, yeah, it's going to slip. And when it does, it just goes. You release it all because of the forces involved. You're pushing it with all your strength, and it's just gone, right? All that energy released. That's what's happening here. Okay? Now, this is actually even better of an example than you know, because what happens as soon as all of those rocks break? Those rocks are broken. Now we have a broken surface underground. What do we call that?
Okay.
It's a linear surface underground where the line was broken into a crack, where all that stress was released from all that bent up elastic energy. A fault! That's how faults are formed. Okay? I don't know whose fault it is, but it's not mine.
Oops.
Okay. Okay, we talked about that. All right, so rocks expend that energy. Sometimes they slip back closer to the original position, but usually they're offset a little bit, right? And you can sometimes tell because you'll see rivers or streams on the surface that do this weird, woo, and now I'm going up here. It's usually because there's a fault underneath of them, okay? And that fault slipped at some point, offsetting the two sides of the river. Okay. We'll talk more about faults here in a little bit. Let's keep talking about the mechanics of an earthquake. Before a big earthquake, sometimes there are smaller movements that occur leading up to it, and then smaller events that occur afterward. We call these foreshocks if they're before, and aftershocks if they are after. Pretty easy to remember that, right? Foreshock happens before, aftershock happens after the main earthquake. Now, sometimes it is the case where you get an earthquake and you're like, oh man, that was bad, right? Like you get a 7.0 earthquake and they report it in the news. And then a few hours later, there's like an 8.1. And we realize, oh, that 7.0, that was a foreshock for the 8.1. Okay, at that point, we would refer to that first earthquake as a foreshock of the next one, the bigger one. Okay, that's how we would classify them to each other, one leading up to the other. And it can occur as a sort of daisy chain of events, okay, where one movement at one point in the fault can cause slippage in the next part of the fault, which causes slippage in the next part of the fault. And so finally, you culminate in a very large slippage of a lot of the fault, okay? Releasing pressure in one area can sometimes daisy chain that event, okay, that chain of events, okay? Now, this is a seismogram, which I'll explain more about here in a couple of slides, but I just wanted to show you what I am talking about, okay? The amplitude of these waves that you can see here on the seismogram is proportional to the amplitude of earthquake waves. The higher the amplitude, the higher the energy, right? Mm-hmm. So check this out. We see this big event right here, right? And then we've got another event here, and another event here, and a couple of smaller events after that. Assuming that this is being drawn this way, So older time is that way. Newest time is this way. Where is the earthquake?
In the beginning?
Yeah, well, the most recent one, right? Here on this side. This is our earthquake. Foreshock. Foreshock. Okay? That's how they'll show up on a seismogram. All right, now let's talk a little bit more about faults. There are 3 types of faults that I want you to know about today. Remember that a fault is a crack, a surface that forms because stress caused that rock to break. At some point, enough stress built up that this fault formed. Now, just because that fault formed does not mean that that stress is just magically gone. It continues to build up again. And this is the #1 rule to remember with earthquakes. Where there is an earthquake, there will always be another earthquake. Maybe not immediately afterward, depending on the amount of stress and how long your fault is. But at some point in the future, there will be another earthquake there. Why? Because the stress that caused that fault to form in the first place is still there and is going to keep building up on that surface again. You following me? Great. So the 3 types of faults, we classify them based upon the motion on each side of the fault relative to the fault plane. Let me explain that here. All of these 3 types of faults that you'll learn about today have a fault plane. In the case of these 2, it's at that angle, and this one is vertical, okay? Right there. On each side of that fault plane, there is motion. The motion relative to that plane is how we tell these apart from each other. The side of the fault that is above the plane of the fault, okay? So if this is our angle of our fault, the side that is above the angle, so over here, I guess you could say it's living on the obtuse side of that angle, okay? We call that the hanging wall. Beneath the angle of the fault, we call this the footwall. Those names are independent of the motion. Okay? I'll explain why I'm being very specific about that in a moment. When your hanging wall is moving down relative to the footwall, so your hanging wall moving down, footwall moving up along the surface of this fault, we call that a normal fault. So in a normal fault, you've got this motion. Okay? Normal fault. In a reverse fault, we still have our hanging wall, same place, still have our footwall, same place, but in a reverse fault, the hanging wall is moving up relative to the footwall. Now I'll explain why I was talking about earlier. It's very tempting to try and remember this as the footwall is the one that always moves down. That is not how this works. Do not remember it like that. The footwall is called the footwall because it is beneath the angle of the fault plane. The type of fault is determined by the motion of the hanging wall and footwall relative to each other. Okay?
You said it was the angle of the what?
The fault plane. This is our fault plane right there. Okay? So if it's at this angle, that side is the footwall. That side is the hanging wall. If I was looking at a fault plane and it was at that angle, this would be the footwall. That would be the hanging wall. Okay? Are we clear on reverse and normal faults? Good. Now let's talk about the third kind, strike-slip faults. When you have a vertical or near vertical fault plane, instead of having up and down motion relative to each other, you have side-to-side motion with each other. They'll move like this. Now, out of curiosity, can anyone point out to me what this is similar to? What the physics at play here are similar to? Not pressure. There's something else we learned about, huh? There's something else we learned about earlier in the course that has interactions between bodies of rock that are very similar to this. In a normal fault, these two sides are moving away from each other, okay, along that plane. In a reverse fault, these two sides, one is shoving on top of the other. And in a strike-slip fault, they are sliding past each other. What do y'all think? Sound familiar in any way? Where bodies of rock are moving away from, towards, or sliding past each other?
I don't know what you're talking about, but I can't remember the name.
That they are moving away from each other?
In one, yeah. Any ideas, Jocelyn? Anything we've talked about in the past where we have interactions between two large bodies of rock where one class is classified by the bodies moving away from each other, one is classified by them moving towards each other, and then the last one is they scrape past each other? How about plate tectonic boundaries? Convergent, divergent, and transform plate boundaries. In a normal fault, the two sides are being pulled away from each other and are sliding down that surface, like a divergent plate boundary. In a reverse fault, the hanging wall is being shoved up on top of the footwall, like in a convergent plate boundary. And in a strike-slip fault, they are just sliding past each other, like in a transform plate boundary. These are the same physics. They are simply not happening on the edge of a plate. They are happening somewhere in the middle, okay? But the same physics at play here, okay? The push, the pull, and the slide. Think of it like that, okay? Just remember that. San Andreas Fault. Y'all have heard about the San Andreas Fault, I'm assuming, right? Even if it's only by watching a certain Dwayne "The Rock" Johnson movie, right? San Andreas Fault is a strike-slip fault. That means it is sliding. So contrary to popular belief, there will never be a time when a large chunk of California breaks off into the Pacific Ocean. That is an urban myth. There is no science behind that because it is a strike-slip fault, not one along which something slides off the other. Okay? It is, however, the largest fault. It is extremely long, going all the way from here all the way up there, pretty much the entire length of California, which is why when it goes off big. When it goes off. Yeah. Which everyone is like, we're due for another one. I mean, okay. This is my problem with saying things like that. This is my problem with saying things like the San Andreas Fault is due for an earthquake. This is my problem with saying things like the Yellowstone supervolcano is due to go off. People say that based upon averages. If Yellowstone went off 10 million years ago and 1 million years ago, then you would say, okay, well, that's two occurrences over 9 million years. Therefore, it goes off every 4.5 million years. That's how people typically think. That's not how nature works. It goes off when it goes off, right? Same thing is true for the San Andreas Fault. Just because it generally goes off by averages about every 150 to 175 years, and the last time was in the early 1900s, everyone's like, we should expect a large San Andreas earthquake in the next 20 to 25 years. That's based off of averages. When you really look at the history of earthquakes, there have been hundreds of years between earthquakes. There have been dozens of years between earthquakes. It's not based on averages. Nature does not care about averages. Just remember that when you read those sensational news stories. Okay?
There's just too many daily processes to really.
Yeah,
understand
I
what's
mean,
happening.
San Andreas Fault could go off tomorrow, or it could go off in 100 years. We watch it as closely as we can to try and tell, but I mean, there's no way that averages can tell us if it's going to go off or not. That's not how nature works. Okay. So how do we study these earthquakes? Well, we use seismographs. Okay. This is a seismograph, and you may notice this looks kind of like that graphic I showed you earlier. It's making a seismogram. Okay. So how does a seismograph work? Well, it is a device that sits on the ground and has a counterweight underneath in the ground. Okay. As energy waves roll through this device, it causes the ground to shake. But because this pivot, this arm is suspended on a near frictionless pivot, as the ground is shaking, the pen on the end of this pivot is staying still while the rotating drum of paper is moving underneath of it, causing this whole thing to draw amplitude waves as the drum rotates around at a consistent rate. The cool thing about this is those amplitude waves that it draws on the drum are directly proportional to the amplitude waves of the earthquake. This, my friends, is how we measure the intensity of an earthquake. The higher the amplitude on the seismograph, the higher the amplitude of the earthquake. The higher the amplitude, the more energy. I'll tell you about that conversion here in a little bit. Now, this is the device that we use today. We've used them for decades, right? However, thousands of years ago, about 3,000 years ago, the Chinese Empire developed their own way to kind of study earthquakes. They had these drums that they would cast out of bronze, okay? And there was a counterweight, and this counterweight was attached by multiple arms to these dragon heads on the sides, and suspended in each dragon head was a little ball just barely sitting there. If at any point the ground started to move because of an earthquake, even if people didn't notice it, the ball, the counterweight would move in the direction that the wave had traveled, and the ball would plunk out of the dragon's mouth and into the frog's mouth. And you hear a loud plunk, and someone would go and check it out and be like, oh, shoot, okay, well, an earthquake happened in the direction that that came from. Send riders out that way and check on our villages, right? They were doing this for a long time, not nearly as accurate as we can get with these, right? And it didn't really give them any context for how strong the earthquake was, but it's still a fascinating deal. I actually have a goal one day of building one of these just for fun. I think it would be cool. Okay. Let's talk about these waves. There are two main types of waves. The first kind are surface waves. Where do you think those happen?
On the surface.
On the surface. Yes, yes. Good. Well done. Excellent deduction. These are the kind that break stuff. Your car flies up in the air. Windows shatter. Buildings collapse. Why? Because the surface is moving. Okay, up and down. Okay, surface waves. Large amplitude. Think of those as the ripples on the surface. Okay? Of your pool as you drop that rock in. Then we've got body waves. To demonstrate body waves, I built a model. I'm a big fan of physical examples whenever I can help it. Okay? Body waves come in two flavors, primary waves and secondary waves, P and S. Okay, that's just what we'll typically call them for short. Primary and secondary. Now, primary waves, those are the kind that are pushing and pulling material, okay? Compression. Compression. It goes through solids, liquids, and gases. All of those things allow the passage of primary waves. So what do I mean? Let me try and do that without turning off my thing. Okay. Watch what happens. Here I have, there we go. Okay. I have a spring. Okay. It's actually a slinky, but it will work, okay? If I provide energy to this spring in that direction, but I do not take it all the way myself, I'm just providing a little burst of energy to this, watch what happens. What do you see happening?
The energy is transferring through the entire thing.
Do you see that zone of compressed slinky that is traveling down that direction? No part of this slinky is actually going down to the end, is it? It's all staying in the same spot. What is changing? What's happening? There is a primary wave, a compression wave traveling through this material until it dead ends right there. That's a primary wave. That happens in the rock too. The compression of rock. That is a primary wave. Okay? Then we've got secondary waves. Secondary waves. That is the up and down motion, side to side, okay, at right angles to that energy. So I just provided energy to that slinky, and that energy traveled forward in the direction the energy was applied from. Watch what happens here. I'm going to try and make this as taut as I can, and then I'm just going to push my hand that way a little bit and then return it to its original position. What's happening to my rope? What direction is it moving as I apply that energy?
Vertically.
Huh?
Vertically.
Vertically. But I'm providing energy that direction. It's deforming. It's moving perpendicular to the direction of energy applied. That is a secondary wave. Both of these waves occur in an earthquake. Compression and motion perpendicular to the applied energy. Okay? Secondary waves, though, those can only go through solids. You can't really move a liquid like a gas, you can't really move a liquid or a gas perpendicular to stress that's applied to them or to energy that's applied to them. They can compress, like for a P wave, but in a secondary wave, they cannot pass through them. That will be more important later on. I'll explain why. Okay? Those are the different types of waves in an earthquake. Any questions? All right. So how can we use all of this information? Okay, well, let's use some seismographs. There is an earthquake somewhere in the world. It's picked up by seismographs all over the world. Let's just focus on 3. The first one is in Nagpur, India, then Darwin, Australia, and then in Paris, France. Let me give you some context here. We're going to figure out exactly where that earthquake occurred based upon the intensity of the earthquake waves that were picked up by these seismographs. The further your earthquake is from the seismograph, the weaker the signal will be. It loses energy over time. That's pretty easy to get, right? So how can we use these 3 to figure out exactly where our location is? Let me demonstrate with an example. This is Zara. Hello. She's just hanging out right there. She hears a noise coming from that direction. She wants to know what that noise was. How is she going to figure it out? Half of her perceived world is in that direction. That's a lot of stuff and a lot of places where that noise could have come from, right? What does she need?
A seismograph.
A seismograph. No. No. She needs more data. She needs someone else to help collaborate with this. So, here's Lydia. Lydia also heard that noise, But from her perspective, it came from that direction. What has this done for us?
Decrease the area of
Yeah, it's eliminated a sizable chunk of the perceivable world where that noise could have come from. Zara heard it this way, Lydia heard it that way. Now there's only about 25% of the perceived world that it could have come from, right? Okay, what do we need?
another person.
Another person, at least one other person. Okay, here's Sebastian. I already had two girls. Okay. All right, there's Sebastian. Now, he heard that noise coming from that direction. What has this done for us?
Eliminate another reach.
Sorry, what?
I'm eliminating another area of possibility.
Yeah, you've eliminated a lot more area. Now that noise must have come within the bounds of these three observations. Do you know what we call this process? Huh? It's kind of like a process of elimination, but there's another name for it. I'll give you a hint.
Triangle.
What about triangle?
Triangle sum.
No. Using at least three sources of information to pin down a location. We call this triangulation. Okay. So, we have seismographs everywhere, right? They're literally all over the planet. There are more being set up all the time. As a matter of fact, I'm in negotiations to have one installed here at Odessa College. It'd be pretty cool. The further away your source of energy is from the seismograph that picked it up, the less intense the picked up waves will be on your seismograph, right? So based on that knowledge, which one of these seismographs do you think was closer to the source of the earthquake wave? India, Australia, France. What do y'all think? Which one was closest? Look how close your first S wave and your first P wave are, right? First S wave, first P wave, first S wave, first P wave. The P waves and S waves are getting further apart. Where do you think? And by the way, less intense, right? India. Yes, India picked up that wave first. I know you said it. I wanted more people to say it. No. Yeah, I know that you said it. I wanted more people to understand why. Okay, which one picked it up last? France, right?
And that's because of the intensity. Right?
Well, yeah, look how much smaller the intensity is, the amplitude, but also look how far apart the P and S waves are. Okay? So how can we use this? There's a formula. Yay! But don't worry, I'm going to give it to you, okay? Triangulation, we use this formula. S time minus P time times 8 kilometers per second. 8 kilometers per second is the approximate speed at which an earthquake wave propagates underground, okay? Ignoring the little things like different types of rock, other features that may go through, that sort of stuff, assuming an average of 8 kilometers per second, okay? So S time minus P time times 8 kilometers per second, what does that give us? If we apply that to the results of these seismographs, then we see, here's Nagpur, India. If we plug that in here, then what we get is, it's so hard to read that on the screen, 3,400 kilometers. So, but there's no directional component. Only a distance. So at any point along this radius of 3,400 kilometers from Nagpur, India, that's where that earthquake occurred. That's a lot of ground to cover, right? What do we need? More data. So Darwin, Australia, right there. We plug the same equation in. What do we get? 4,900 kilometers. And now we have a second radius. Where could this earthquake have occurred now? By having a second point of data, I have narrowed it down to two possibilities. Where are they? I know that it has to have happened somewhere on that radius and somewhere on that radius. Where are the two places that could have occurred? I'm not asking for a name of a place. I'm asking for you to tell me where on this shape it could have occurred.
In between both circles.
Where the two radii intersect. Bingo. What do we need? One more data point, at least. The more the better, but one more at least for triangulation to work. So Paris, France, we plug in that number. I think it's like something like 8,400, something like that. It's huge. And we throw that radius in, and now we know which one it was. Boom, the earthquake happened right there where all three radii intersect with each other. This is triangulation using seismographs. This is why the entire world hears about earthquakes and where they happen only minutes after they do. Because it takes only minutes for seismographs around the world to pick up that earthquake wave and then send this information into all the news sources. Okay? Now, there are a few places in the world that don't cooperate. Iran doesn't share its seismograph data. Surprise, surprise. North Korea, again, surprise, surprise. But, I mean, we can usually get what we need without their data. So that's okay.
Are you being vengeful, Mr. Hart?
Am I what?
Are you being a little dismissive?
A little dismissive. Maybe a little. That's okay. They piss everyone off. All right. Now, how do we measure earthquakes? How do we differentiate them from each other? How do we classify them? Well, there is this scale called the Mercalli intensity scale. This goes from 1 through 12 and is based entirely upon the damage inflicted by the earthquake. So at 1, there's little to no damage, and on 12, it is total devastation. While this is useful in some areas, why would this not be useful for science purposes? This is great for FEMA, for the Red Cross, for governments. If you hear there was a Mercalli 11 in Chicago, you're like, oh, crap, that's a lot of damage. That means something to you as a government official. Why would it not really make much of a, why would it not mean much to me as a scientist if I study earthquakes? I like where you're going with this.
Because it's relative to the destruction of like everyday people, right?
Yeah, it has to do with entire, I think that's where you were going. It has nothing to do with actual scientific reference. It's based entirely upon what has been built there. What if the same earthquake happened in the middle of the Serengeti in Africa? A few huts get knocked down and some giraffes get scared and run off. Might call that a Mercalli 1 or 2, right? It does not mean the same thing everywhere. And so we can't really use it as a scientific reference.
Yep.
Instead, we use the Richter scale.
Yay.
The Richter scale is logarithmic. That means that it has increasing orders of magnitude, 1 through 10. We have never experienced a Richter 10. Theoretically, there shouldn't ever be a Richter 10. Closest we've ever gotten in recorded history was a 9.4, 9.6. think that one was a 9.6 in Chile in 1960. Okay? Largest earthquake we've ever recorded. Incredible amounts of devastation. Now, when I say that it's logarithmic, that means that it increases the order of magnitude, not of the energy released, but of the amplitude. So the amplitude of a Richter 1 moving to a Richter 2, we are increasing the amplitude 10 times. Moving to Richter 3 is 10 times the amplitude of a Richter 2 and 100 times the amplitude of a Richter 4 or a Richter 1. Okay? That's how this is working. Easy. And universal, no matter where in the world you are or what cities are on top of it. Okay? Now, how does energy relate to that? Well, the conversion from energy to amplitude is roughly about 32 times. So one magnitude increases by about 10 times the wave amplitude by about 32 times the energy released. So by the time you get up here, we're talking some incredible energy. A Richter 9 earthquake has the same energy as, let's count this. Let's see, that's hundreds, thousands, millions, billions, 1.8 trillion kilograms of TNT high explosive. If you want some reference here, the Hiroshima atomic bomb, that was one of the 2 dropped to end World War II, right, had the same energy release as about a 6.2 earthquake. The largest nuclear weapon ever tested, which I told you about early on in the class, the Tsar Bomba, right, that was about an 8.1 in energy released. And the largest volcanic eruption in recorded history, which is Krakatoa, supervolcano eruption, released about as much as an 8.5 earthquake would. This is a lot of energy when you get up there.
Why does Chile receive so much?
Why does Chile receive so many earthquakes? How about I go to the next slide and show you? Okay. Here we have an earthquake heat map. Everywhere you see that is red is where we get a lot of earthquakes. Where do they mostly happen? What belt? Well, we've got the Alpine Himalayan. Yes, that does have its fair share, sure. The Circum-Pacific more than anything. We also, this happens to correspond with the Ring of Fire, called so because of all the earthquakes. The Circum-Pacific mountain belt also has tons of earthquakes, okay? Here's Chile. Look at all those earthquakes. What's happening here? Why are the Andes there at all, that mountain range? Because the Cocos Plate and a couple of other plates and the South American Plate are running into each other, and they're all subducting underneath of South America, making that oceanside mountain belt. Okay? Very, very active zone. Lots and lots of pressure from that subduction. Yeah, poor people. Chile. Yes, if you're going to Chile, make sure you pack a sweater. Okay. So, some types of destruction that are related to earthquake activity, as you can imagine, there's a fair amount. Okay. The waves themselves, very destructive. Buildings are not meant to move up and down and side to side and shake and do all of this, right? You can build them to be a little bit more able to withstand that, though. For example, a building made out of metal and glass and concrete, how well is that going to shake or flex? Not very well, and so it's going to collapse. What about a building made of wood? Wood flexes and bends all the time. As a matter of fact, the older wooden buildings tend to survive earthquakes better than the newer glass and metal ones. Yeah. Huh? And absorbing? Not so much absorbing as much as it is flexing with the movement of the ground. Okay? Like a tree would. right? You can build like a large building in some cases, and they're actually doing this in California. It's very expensive, but there are several ways to build a building so that it can move with the ground. I saw a design once where you can build a skyscraper so that it is sitting on top of what are essentially massive ball bearings in a socket. And because it is sitting on top of these ball bearings, as the ground is moving, the building basically just stays still as the ground is moving under it because it is rolling on these ball bearings.
Whoa.
Yeah. Now, this can go wrong in a lot of ways. If something were to inhibit the movement of those ball bearings, all of a sudden you've got some torque on your building because one ball bearing isn't moving. And so it could end badly. I don't know if that design was ever implemented. It was a really cool design that I saw once, though. There are ways that they're developing to make, they call them earthquake-proof buildings. Nothing is earthquake-proof. I don't think anything is anything-proof, really. One of my favorite sayings, I do not remember who said it, nothing is foolproof to a sufficiently talented fool. Right? And it's the same thing for earthquakes as well. Okay. If you ever do build a house, please make sure you build it on bedrock. If you build it on loose sediment like sand, you are subject to something called liquefaction. Liquefaction is when the ground is moving because of an earthquake, and that movement causes the groundwater to rise up to the surface, basically turning your loose sediment into mud. And if you don't think that sounds bad, just ask the person that owned this vehicle.
Oh.
Yeah, during an earthquake, the ground turns to mud, stuff sinks into mud. Buildings, cars, people, houses, all of it. I've seen pictures of apartment buildings where the first 2 floors, the first 2 stories of these apartment buildings had sunk into the ground. Because while it's shaking, the sediment is being disturbed, and the groundwater has risen, the ground is basically behaving like a liquid. Stuff sinks into it. And as soon as the shaking stops, boom, back to solid ground. Whatever got stuck, whatever got sucked in, stuck. That used to be the street, and now his car is stuck in it. Liquefaction.
A poor little Toyota.
Huh?
A poor little Toyota.
Yeah. Come on now. Don't be like this. Okay. All right, so some other things. Landslides. Earthquake shakes, and it disturbs your angle of repose, right? The angle of repose is disturbed. Stuff's going to fall off your slope to reach that angle of repose again. And so landslides will often occur as a result of earthquake activity. Fires. Think about all the gas lines and electrical lines and all of the toxic chemicals that we keep in our cities. If you break the ground, if you have an earthquake, you're going to break those gas lines. You're going to break those power lines. And those are 2 not very good combinations. In the San Francisco earthquake, back in the early 1900s, the city got lit on fire. Okay? City's burning. They decided they were going to try something that we call a controlled burn. Whenever there's a wildfire, like out in a forest, and they have no hope of containing it, what they do instead is they burn themselves a strip of forest or grassland around the out-of-control fire. They're literally sacrificing a ring of nature, of ecosystem, of all of that to save the rest of it. Because once the wildfire, the out-of-control fire reaches that ring of already burned stuff, there's nothing for it to burn and it dies. It doesn't jump to the rest of the saved woodland. Okay? That's called a controlled burn. They decided to do that in San Francisco. They did a controlled burn in the city to try and keep the fire contained. But they lost control of their controlled burn and ended up burning most of the city down. Yeah. which is why when you go to San Francisco, it's relatively rare to find a building that is older than that earthquake. They had to rebuild pretty much the entire city. And then there are tsunamis. Yeah, a tsunami is what happens when an earthquake occurs offshore and displaces some seafloor. So if I have, here's my fault, okay, between my two hands, imagine this is the surface of my fault. And then I get some movement along that fault, which causes, say, that to happen. Then all the water above that seafloor goes down with it, right? And all the water above this part of the seafloor is still at its original height, which means that it's going to rush that way to try and level the surface of the ocean again. And however much displacement there was here, you're going to get that high of a tsunami over here going that direction. I have a graphic here. I really hope that it works. I don't think it will. Okay, but that's what happens basically. Seafloor is displaced downward or shoved upward. In either case, there is displacement, displacing the water above it and making that water rush in either direction, depending on what happened there. Now, in 2004, on December 26th, it was the day after Christmas. I remember this day vividly. I was living in Boston, Massachusetts. I was, 11 years old. I was playing with my toys. You know, it was the day after Christmas. I got some new toys. I was just playing with my toys. My parents were watching the news. I wasn't paying too much attention to it. I knew that something bad was going on, but I wasn't really paying attention to what. My dad gets a phone call, packs his bags, and I didn't see him again for 6 months because he was in the Navy. He was deployed to Indonesia to help with the relief effort because there was a massive 9.4 earthquake in Indonesia, and it caused a tsunami 33 feet high. Most of the islands in Indonesia are not 33 feet above sea level. What does a 33-foot wave do to an island that is not 33 feet above sea level? This is live footage from that day, taken from the 3rd story of a building.
Flood the entire island.
Bless you. Bless you. When the ocean comes to say hello, it takes everything with it.
On an island.
Was it 3rd floor?
What? This is the 3rd floor. Entire islands were scraped clean of civilization. My dad spent those 6 months on a helicopter, basically going island to island, looking for survivors. His specific job was teaching them how to purify their water. What happens to every source of fresh water on an island if the ocean comes to visit?
Contaminated.
It's contaminated with ocean water. There wasn't a spring, there wasn't a stream, there wasn't a lake, there wasn't a reservoir. There wasn't any source of fresh water on most of these islands that didn't have salt in it now. So he was going around teaching the people on the islands how to purify their water so they could actually drink it. A lot of people died from lack of fresh water after this. Huh? How do you? Well, the simplest way is to evaporate it. You need to set up a mechanism to evaporate that water so that the salt stays behind and you can collect the fresh water off of the droplets that form afterwards. You get a bucket of salt water and you suspend like a tent of clear plastic above it, and then you put little receptacles like smaller buckets or containers around the edges of that tent of plastic, and then you set that water out in the sun. By the end of the day, you know, your water has evaporated out in the sun. The fresh water is collected on the underside of the plastic and drained off into the smaller receptacles on the side. It's a very basic way to do that. He was helping them set up more permanent solutions and teaching them how to do all of this and how it worked. I believe last count, more than 400,000 people were killed in this. The earthquake didn't kill them. The tsunami did. And the lack of resources afterward. He would go to islands that were supposed to have thousands of people and several villages on them, and there was nothing there. Not even a trace that any humans had ever lived there. He would go and visit other islands, and he would find more people had died on those islands than were surviving. There weren't enough survivors to bury their dead, and so they had just piled them up. Just piles of dead. There were too many to bury and not enough people to do it. They had to worry about their own survival, so they just piled the dead people up, and the animals were eating them. This is a serious deal. So we care a lot about making sure that we know where these could potentially happen. Okay, not only earthquakes, but also the results, like a tsunami. We spend a lot of time trying to figure this out. Okay, so we monitor these like hawks. Whenever there is an earthquake-prone fault, we are on top of it as best as possible. Geologists specifically dedicate their careers to watching these things. Okay, this can be tricky though, because as concerned as we are with letting people know when there is something dangerous that will happen, sometimes other things can get in the way. A lot of geologists have been let go from their jobs because they predicted something that didn't happen. They warned the people. It was a boy that cried wolf situation. Okay? Hey, something's going to happen. Evacuate the city. City gets evacuated. Nothing happens. Well, you're obviously not very good at your job. See ya. And so as a consequence, other geologists tend to be a little overcautious before sounding the warning. This isn't always great. In 2009 in Italy, there were some geologists that suspected there would be an earthquake. Didn't give out the warning enough time because they wanted to collect more data beforehand. I remember if it was an earthquake or a volcano. They wanted to collect more data beforehand. And because they wanted to be extra double sure the event happened before they could get the warning out, people were killed, damages, all of that. And when it was found out that they could have warned people but didn't because they were trying to collect even more data, they were sent to prison for manslaughter. Because it was deemed by the court that the people who died were on their heads by not having given the warning. Okay. They were worried about their jobs, which is understandable. So where do you draw that line? It's tricky. You want to do what's good for the community and you want to do your job, but you also want to keep your job, right? So next time you meet a seismologist or a volcanologist, say thank you. They deal with a lot. Okay. Now, we have learned from these earthquakes some very cool stuff. Remember I told you that S waves will not pass through liquids, but P waves will? Well, using just that basic fundamental principle, that is how we have been able to come down to some pretty firm conclusions about what the inside of our planet looks like. We artificially make P and S waves, send them down through the ground, and we can get some cool stuff off of that. For example, these waves interact with different materials in different ways. They will either reflect, which means they bounce off the surface like this, right? Refract, which means that they will encounter that new surface, that new material, change their angle, and then go back to their original angle once they reach the other side. Or they will diffract, which means that they encounter the new material and kind of just ride the edge of that material until they can continue on their original course. Using those three interactions that these waves have with different materials, that is how we've been able to figure out that we have a solid mantle, liquid outer core, and solid inner core. It's pretty cool. If you have a hard time imagining refraction, just think about a straw in a glass of water. You ever held a glass of water with a straw up and you've seen that the real straw that you see in the air is offset from the straw that you see in the water? That is refraction of light. The wavelengths of light passing through the water are sending your eyes an image of that straw in a slightly different location because it is reaching your eyes at a different time and at a different angle than the light reflected off the straw in the air is. That is refraction. Okay?
How do they know you refracted, like if it came back the same angle?
Well, it's not always the exact same angle, but even if it is, the fact that it went at a different angle in here means that it's going to come out at a different place, right? So if it went in at 45 degrees here, switched to 75 degrees, and then went back to 45 degrees here, it's still going to come out at a different place than it would have. Okay. Let's talk a little bit more about plate tectonics. Let's wrap this up with a little bit of plate tectonics. Before our current understanding of plate tectonics, there was something called continental drift. Now, continental drift, unfortunately, is still taught in a lot of schools. We've known better since the 60s. The plate tectonic theory became accepted by the scientific community in 1968. And yet a lot of public institutions still teach continental drift, which is basically that our continents are gigantic islands floating on a sea of magma underground. How many of you learned that in school? Okay, a lot of people, okay? That there's nothing but liquid rock underneath of the continents. You know better now if you've taken my class, right? We know it's solid all the way to the outer core. That is tectonic plate theory. Not that our continents are just islands playing bumper cars with each other on a sea of molten rock, but that they are being driven through solid convection in the mantle. How do we know that our continents have been moving and interacting and connecting and all of that from each other? Well, some of them, it's pretty obvious. You can see how easily they fit together, right? As a matter of fact, there are several places on the east coast of South America and the west coast of Africa where the layers of rock and the fossils in those rock add up perfectly. Like puzzle pieces. They fit together. Because at one point it was one continent that split apart, thanks to our current understanding of plate tectonic theory, right? Also, the fossils, there are several fossils that are present on every continent. Glossopteris is a plant you can find in Australia, Antarctica, India, Africa, and South America. How would that have happened unless they were connected at one point? Okay, same thing with a bunch of other fossils. We will learn more about these things in 1404 if you're taking that class with me. Okay, we talk a lot about this. We go over all the supercontinents and the things that lived on them. It's really fun. I'm just going to remind you real quick how convection works. Convection is the movement of hot material upward and cold material downward, constantly cycling up and down and up and down and up and down as it heats up and cools off in the mantle, still staying solid for the most part, right? But as it's doing this slowly, and this happens over millions of years, remember, okay, it's creating that drag underneath of our continental plates, and that's what's pulling them and pushing them and scraping them and creating those different boundaries. Convection. Now, based upon our current trajectories of tectonic plate movement because of this convection, we can make some models about where we think Earth's continental configuration will be in the future. In about 50 million years from now, we expect Africa to have finished its collision with Eurasia. The Mediterranean Ocean is gone. Sorry, Greece and Italy. You're now a mountain range. Okay? Gigantic mountain range here, probably similar in height and size to the Himalayas over there, right? Perhaps even more so because these are much larger bodies of rock. Mediterranean Ocean's gone though. Okay? South America and North America, they split apart from each other. Panama's gone. These two oceans connect again. Okay? Australia has continued moving further north because it's riding on the same plate movement as India. Okay, it's kept moving further north. Where's Antarctica? Yeah, it's still hanging out down here, right? Okay, what about 250 million years in the future? In about 250 million years, it might look something like this, where once again, North America and South America have joined up, but they have moved east collided with Africa and squished the Atlantic Ocean and the Gulf of Mexico into this kind of inland ocean now. Australia has finished its movement north, squishing Micronesia and Indonesia between itself and Southeast Asia. And we have a new supercontinent, which they have given the super real, incredibly inventive name of Neo-Pangea.
Wow.
I know. They put a lot of thought in that one. Where's Antarctica?
Still not there.
Yeah, it's still down there. Why is it still down there? It hasn't moved in like 50 million years, so we have no idea where it could possibly move in the future. It's just sitting down there. As far as we can tell, there are no convection cells underneath of Antarctica at the moment causing it to move. And because there's nothing that's actually causing it to move right now, we have no idea of where it could end up in the future. So all our models just leave it down there.
And it'd be like a cycle. It's gonna separate again.
Oh, absolutely. Yes, yes. This happens over and over and over and over again. And we will go over all of that in 1404. You'll see how everything comes together and breaks apart and it comes together and then breaks apart again and then comes together and breaks apart again. There are entire continents that have existed that don't exist anymore. It's entirely possible that one or more of the continents that we see in you can still kind of recognize the shapes here. It's entirely possible that these shapes will be, and actually very probable, these shapes will be entirely different. Shorelines will change. Stuff will break off. Madagascar broke off from India, right? East African Rift, they don't even show the East African Rift finishing here, creating that separate continent of East Africa. Who knows if that will finish? Who knows if it won't, right? This is intending to send a message, not so much relay direct accuracy, right? Perhaps I should say this is accurate. It is not precise. Make sense? Cool. Now, this is the last thing, and then we're going to end for the day, and I'm going to tell you about lab exam, and then we can move into the lab exam, okay? There are some rocks that have magnetic properties. What would make them have magnetic properties? The presence of iron. Did we learn about a rock that is made all the time in the ocean that has a high quantity of iron?
Basalt.
Basalt, exactly. Well done, guys. Okay. Basalt, high quantity of iron. When those iron minerals are forming in that rock, they are going to orient themselves to magnetic north. Okay? They are formed towards being pulled like the compass of a needle towards magnetic north. Some time ago, I don't remember exactly when they figured this out. I feel like it was somewhere between the early and mid 1950s. They were doing studies from the bottom of the ocean, and they realized that there were strips of basalt along the ocean floor where these magnetic minerals were pointed north, and then another strip where they were pointed south. And then it would return to north and south, and north and south. And they realized that these strips coincided. They were parallel to these divergent plate boundaries where the basalt is being made. So at one point in time, if magnetic north is in its current orientation, they're all pointed that way. But then at another point in time, all the basalt being deposited there is pointing, the magnetic minerals are pointing south. And then we'll go north again, and then south. Through time. The further away from that divergent plate boundary you are, the older the rock is, right? The closer you are, the newer the rock is. So what does this tell us? Earth's magnetic poles switch. I don't know how familiar you are with magnetic poles. How about magnets themselves? You know the concept of if you hold two magnets and you try and put them close together, they will only attach to each other if if the negative pole and the positive pole are approaching each other. Negative and positive attract each other, right? What happens if I flip one of those magnets around so I have a positive and a positive? What do?
Repel.
They repel. Same with a negative and a negative. Only a positive and a negative attract each other. Our planet has a magnetic field generated by the interaction between our solid metal iron inner core and our liquid metal iron outer core. That magnetic field protects us from the vast majority of solar and cosmic radiation. It makes a shield around our planet that keeps us from getting burned to a crisp and our atmosphere from being blown into the universe. Okay? That's what happened to Mars. talk more about that in 1404. Okay. One half of our magnetic field is negative, and the other half is positive. Well, I shouldn't say half. In reality, there are negative and positive poles everywhere. But what we refer to as the North Pole is currently in the northern hemisphere, and the South Pole is in the southern hemisphere. That's not always the case, though, as the rocks prove. Every now and then, they do that. And then they do back to this. And then they do this. What causes this? We're still trying to figure that out. What happened? That just randomly fell over.
I might have accidentally tapped the table.
Oh, well, then I didn't put it on there very carefully. It's okay. I'll fix it later.
I apologize.
You know, it's okay. It kind of broke, but that's all right. What was I saying? Oh, yes, this. Okay, so why this happens, we're not entirely sure. There are a few theories. None of them have really panned out to much with a lot of evidence.
As long as the planet's not rotating.
The planet itself isn't doing this, just our magnetic field. Now, this is happening right now. We are actually in the middle of a magnetic field reversal. When you, let's see, how old are y'all? How old are you? 21? Okay, I'm 33, right? Or I'm not 33, I'm 30, okay? When I was born, when you were born even, the magnetic poles were a lot further north and south than they are now. Everyone takes for granted that when you look at a compass, your needle is pointing north, right? To the northern pole, the North Pole where Santa lives, right? He lives at the North Pole, right? Yeah, it's the North Pole. I was like, isn't it the South Pole? No.
Aren't you a father?
Huh?
Aren't you a father?
Yes, I am. Okay, he lives at the North Pole. The North Pole isn't there anymore. Magnetic North Pole is about middle Canada right now. It's not at the top anymore. It's about the middle of Canada. And it's moving further south at an increasing rate. Right now, it's about 80 to 90 miles a year. It's moving. It's getting ready. At some point, we're going to hit what I'm referring to as an inflection point. In math, an inflection point is when a curve makes its first change into a new curve, right? Like right there where it actually changes its direction, that's an inflection point where now it's a new curve. At some point, we are going to reach an inflection point and it's going to snap into its new orientation. And our compasses will point south. So, is that only going to affect very basic directional stuff? No. What about all our navigation equipment? What about every GPS? What about every satellite? Our magnetic field is going to be in chaos. How much extra solar irradiation is going to come through? What will it do to our technology? Every hard drive we have is written using magnets. Those magnets were written under our current magnetic pole orientation. Will our hard drives even work anymore? I don't know. Some things are pretty clear. Birds are going to be messed up for a while. Whales will be messed up for a while. Anything that uses magnetic poles to orient themselves and to migrate, they'll be messed up for a while, sure. What it's going to do to our technology, I think it's going to be pretty chaotic. I cannot say how much. I think it's going to be bad, but I don't know how bad. And it's something no one's even talking about. Don't know when.
This is the first time I've heard of it.
Yeah, exactly. It's not something that most people are talking about. To be fair, it's entirely possible that it might not be a full reversal. What we've seen in the past is sometimes it'll do this and then go back, kind of wobble back and forth. It doesn't always commit and snap to a new orientation. But if it did, oh boy, that's the situation I'm talking about. Right now, it's moving. Whether it will complete that transition, we don't know.
Like in a million years?
I don't know. These usually don't happen over the course of that long. There have been some that lasted hundreds of thousands of years, and there have been some reversals that only lasted 5,000 years. Okay, yes. Angel won't be alive. So it doesn't matter, guys. Okay. Okay, that's all I've got for lecture today. Any questions about what we talked about?
No, sir.
Okay, then let me give you some info about the lab exam. You cannot use former lab activities. You can use your notes and the Excel spreadsheet. That's it. Should be plenty. If you need more than that, you may not have spent enough time on the labs. Okay? I'm going to be taking all of the test kits that are on the tables, or the lab kits that are on the tables, and taking them away. And then I'll be handing out physical copies of the lab test to y'all. My online students, you have access to them in the lab exam on Blackboard. It should be in week 7, the week 7 folder. It's 12 samples, 3 minerals, 3 sedimentary rocks, 3 igneous rocks, 3 metamorphic rocks. And I tell you which is which. I say, this is a sedimentary rock. Give me these properties. I tell you what properties that I need from you. Okay? Yes?
So you said we can use our Excel spreadsheet and what else?
Your notes.
No.
Yep, Excel spreadsheet and your notes. And also, I give you a Word bank. It's kind of redundant since I let you use the spreadsheet. But there is a Word bank. It's a Word document that has a list of all the possible minerals and rocks that could be on the exam. I give you the names of the answers. It's on you to remember how to find which is which is the point. It's really unrealistic of me to ask you to tell me what these things are without any resources. That's the way that I learned. But I mean, even how long ago was this? 10 years ago when I got my bachelor's degree. It was almost 10 years ago when I got my bachelor's degree.
Whoa.
The world was way different, right? So it's unrealistic of me to say, I want you to be able to tell me all these things without using these resources, when the resources are at your fingertips. And if any of you did go into geology as a career, fingers crossed, it would be unrealistic for any employer to tell you, no, I need you to do this assignment, I need you to do this project without looking at any research. And no one's going to do that. They want you to do the best that you can with the resources available at the cheapest cost to them, right? So it makes no sense for me to test you in a way that is not realistic in that light. So I give you a lot of resources, but I also expect you to obey my rules. Don't collaborate with each other, please. This is a test of you. It's not a test of one person who does all the work and everyone else copies off of them, right?
Yes, sir.
And then also, please use your work, not mine, right? That's really what it comes down to. Ideally, yeah, because again, you've got that time limit. And you really should take it in the rest of this class period. And you've got an hour and a half, right? So it should be plenty of time to take 12 samples. Good?
Yes, sir.
All right, then I will end the recording here and I will open the exam.